Okay, so the formula we have learned, the functions we have learned like during year 11 and year 12. Let's think about what we have learned. Start from year 11, let's say we have linear. Okay, just write it here. We have learned linear, well, let's not say linear, like all the polynomials. And then in year 11, chapter 4, we have learned hyperbolas, truncus, square root. And while circle is a special one, we don't really think about the differentiation of circle in method. We learned that in spec. So we skip circle. And then what we learn in chapter 13, I think, is exponential and logarithm. Exponential and log. And then chapter 14, the last thing we learn is circular functions. Okay, we can see all of those ones. We can either do it to the form of x to the power of n, like square root is x to the power of a half, while truncus is something to the power of -2, hyperbola is something to the power of -1. They all can be done by x to the power of n, or we learned chain rule yesterday is gx to the power of n. We can use that one as well to differentiate that directly. So what we haven't really learned is exponential, logarithm, and the circular function is sine, cosine, and tangent. So all the functions we have learned, we just have exponential, logarithm, sine, cosine, tangent, 5 things to investigate the differentiation formula. So if you can look at the table here, the left-hand side is the simplest version. Okay, only got x, like sine x, cosine x, tangent x, how to simplify. Well, exponential ex and log ex. Well, this is actually 3 exercise. Okay, this is actually 3 exercise. I combine that as one. So it's just formulas, and you just need to remember them. If we can see the simpler version here on the left-hand side, just let you know, for exponential and logarithm differentiation, you can only use this formula to differentiate with base e. Okay, nature base. If you have like log 2x, you can still differentiate that, but not use this formula. Okay, not use this formula. You need to adjust that a little bit first, or change the form a little bit. I'll show you the question later. But this formula only works for base e, like e to the power of something, log e something. And then sine, cosine, tangent. Well, we can have a look. So constant, well, I put everything here. So constant will give you differentiation 0. So what exponential derivative gives you? The e to the power of x will still give you the same derivative, like still looks the same. So e to the power of x, the derivative won't change. It's still e to the power of x. But this formula only works when this is x. Okay, when you have 2x, that's different. Okay, we have 2x, that's different. It only works for e to the power of x. That's the simplest one. But if you have some equation like not x on it, so e to the power of gx, what if we have that? The derivative for that will be g dash x times e to the power of gx. So what you will do is you derive the top, and then you still have the identical thing there, like still have the same thing here. I'll show you why it's like this. I'll show you by using the chain rule. So if we have y equals to f of gx, okay, don't look back to the previous page. What's dy dx equals to? What's dy dx equals to? G dash x times f dash gx. Okay, good. That's the derivative for a composite function. Now let's consider we have y equals to e to the power of gx. Can you see my fx is actually e to the power of x, and then you have a gx to put into that, so it's f of gx. So this is f of gx. So fx is e to the power of x. And then let's apply this formula here. Let's apply this formula here. So 3 component dy dx is 3 component. So the first one is g dash x. What is g dash x? G dash x is g dash x. Okay, we don't have the formula for g dash. So it's g dash x. And then the next thing we will have is f dash of gx. So what is f dash x first? We need to think about what is f dash x. So fx is e to the power of x. So f dash x is still e to the power of x according to the left hand side, this one. Okay, still give you the same thing. So that's the simplest version. E to the power of x will still give you e to the power of x. Now, what's the f dash gx? That's e to the power of gx, right? What's f dash gx? You put gx into the f dash x, you still have e to the power of gx. That's why e to the power of gx will give you a derivative as g dash x and e to the power of gx. That is actually use the chain rule to find this formula here. But you don't want to use chain rule all the time. Okay, you don't want to every time you see something, let's write fx equals to that, gx equals to that, and then g dash x after that. Like, it's too long to do it and it's too slow. So what I recommend here is you just remember right hand side. Okay, you just remember the right hand side. As I said, we don't really use this formula unless we don't know the function. Okay, we don't know what is fx or we don't know what is gx, then we use it. Otherwise, we will directly apply the formula here. Okay, we directly apply the formula here. So if you can remember the complex version, well, it's very easy to get the left hand side. Okay, so it's very easy to get the left hand side. When you derive, the x is just a 1. So it's easy to do if you remember the right hand side. So this is something you need to remember. Okay, this is something you need to remember. So for e to the power of something, we derive the power and we repeat the original function. Okay, we repeat the original function. And what is log e gx? Okay, the log function is very interesting. Can you see polynomial, when you derive it, still become a polynomial. Exponential, you derive it, still some kind of exponential. But for and you can see the circular function below here is still circular function when you derive it. But for log, when you derive it, it's not looks like log anymore. So if you have log e something, okay, log e something, what the derivative looks like is you derive the inside and then put it over the inside itself. So you derive the inside and make it a fraction over the inside. So it's g dash x over gx. So you don't have log e at all. Okay, just log e disappeared. Well, sine function. So we can see the pattern. Sine, cosine, and tangent with some gx. We always have a g dash x in the front. Okay, we always need to derive the inside. Can you see? Doesn't matter what kind of formula, like log e or exponential or circular functions, we always derive the inside first, like a g dash x first. And then what we do is sine will become cosine. Okay, so there are pairs. Sine will become cosine, but cosine will become negative sine. Okay, cosine will become negative sine. So you can see there's a negative here. So we derive the inside. Sine become cosine. Cosine become negative sine. And you still have the gx. Okay, you still have the gx. You can see for exponential, we still have the gx. For log, we still have the gx. For all the circular function, we still have gx insert into the function. And tangent is a little bit interesting. Tangent will become secant squared. What is secant squared? Okay, what is secant squared? I'll write it here. Secant x equals to 1 over cosine x. Okay, what is secant? Secant x is 1 over cosine x. That why you need to know this, because you need to evaluate sometimes. For example, derive the tangent and then evaluate like what's f dash pi on 4. So you need to know what that looks like. You don't know how to evaluate secant, but you know how to evaluate cosine pi on 4. Then what is secant squared x? Okay, secant squared x therefore is 1 over cosine squared x. But we put the 2 as the power, okay, in the middle of cosine and the value. Why it's like that? I think it just looks more beautiful. So we can write it into this way. Okay, they are equivalent. So it's actually the power, but it's easy to put in the middle because we don't know it in the square bracket outside that, and it looks more neat, I think. So it's actually cosine to the power of 2. It's the cosine to the power of 2. So that is second squared x. Well, second squared gx, instead of x, we put gx in. That's it. Okay, so that's just the 5 new formula we have learned. Let's just don't look at it, have a think about it. Yes? No, you don't need to ask to sketch it. No, not the sketching. Special student learn the sketching, not method. Okay, let's just not look at this and have a think about what all the derivative looks like. Okay, exponential, so e to the power of gx. Okay, exponential is the one who remain the same, who always have the same thing. So doesn't matter is exponential, logarithm, sine, cosine, tangent. We always need to derive the gx first. So exponential is the one who remain the same. So we derive the power and then we copy the function again. That's exponential. The second one is log. Okay, so log is the one who looks not the same as before. So we don't have log anymore. So it's the fraction one. Okay, it's the fraction one. So we derive the inside and then we put that over the same thing. We always have gx. So that must be the g dash x over the gx. So sine will become cosine. So we'll derive the inside, make it g dash x, and sine become cosine. So it's a cosine gx. So cosine gx, we derive the inside, so g dash x. Cosine will become negative sine. So it becomes a negative g dash sine gx. And then tangent is the little bit special one, so it becomes second squared. Okay, that's the only one becomes second squared. So it's g dash x second squared gx. Okay, so that's the 5 new rule. So I think we can just remember this lesson. So we will apply those formulas into calculation. Let's have a look at the calculation here. Well, I'm not going to show you the chain rule one by one. So if you just remember that, the chain rule is just use this left hand side combined with this formula here. So it's all the same. I don't need to show everything for you. We just need to know how to use it. Okay, let's have a think about the derivative. Think about the derivative below. Okay. For the first one, let's try not to go back to look at the formula. Okay, let's try not to go back to look at the formula. So it's e to the power of gx. Have a think what you should do. Okay, you quickly write the answer, what you should do. So e is the one who remain the same. Okay, e is the one who remain the same. You always need to derive the gx. When you finish, you can just have a look if you have the right thing. We derive the power. So when you derive the power, that gives you 2x minus 4. And then you copy the thing again. Okay, copy the thing again. Okay, that's the first one. Second one is still exponential, but obviously we can't do that because it's times and divide, which looks very bad. I don't want to use, well, remember, even though you know how to use quotient rule now, that's the thing we want to avoid. Okay, if we can do something else, we don't use quotient rule because quotient rule will become very messy in the end. You have a lot of components and have the square at the bottom, so we're trying to avoid that. We will think first, is there any other way we can do this? Okay, so what we can do first to make this equation looks better. what we can do. Yep. How to the power of negative x to the power of 2. Yeah. And how about the top? Top is still in the times form, like still something times something. Expand. Good. So let's expand. Well, what's the expand form for the top? Let's expand first. E to the power of 3x. Good. So we add the power. Okay, we add the power. Same base, we times them, we add the power. So a to the power of m times a to the power of n, that's a to the power of m plus n. So we need to add the power. And then what we have plus 3 e to the power of x. And then we divide the e. Well, if you say we can, well, I can either separate them as the fraction, that divide by that and that divide by that, or I can say that times by e to the power of negative x to the power of 2. Flip it to the top. Okay, so what we have now? Expand. What's the expand form? E to the power of 4. Well, how you can combine that? 3x minus x squared. And plus e is 3ex minus x squared. Have a question. Well, it's not really related to this question. E to the power of x to the power of 2, is that equals to e to the power of x and then to the power of 2? Are they equivalent? Why are they not equivalent? What's the second one equals to? Okay, this equals to e to the power of 2x. Okay, this is not equivalent. They are equivalent. Okay, e to the power of x to the power of 2 is x to the power of 2 is the whole power. Okay, it's the whole power. So it's not the same. Do you know what this equals to? This equals to e to the power of x and then to the power of x. Okay, it's e to the power of x times x. That is e to the power of x to the power of 2. Can you see the difference? Now let's derive it. So f dash x equals to, derive the top 3 minus 2x times, repeat the same thing. Okay, you repeat it again, copy it, plus 3 times 1 minus 2x and times the same thing. I'm not worried about the simplification. Can't really simplify it. Well, you can expand it, but not make any difference. So I'll just keep my answer like this. This question is about the expansion. Okay, it's talking about the expansion, if you can expand it. So it's talking about the expansion. Okay, fx equals to square root e to the power of 2x minus x. What I should do? It's still exponential. What I should do? What you can do to the square root? Yeah, make it to the power. So fx equals to e to the power of 2x minus x, and then to the power of a half. Yeah, and what rule we can use now? Chain rule. Okay, what is which chain rule we use? We have the f of gx and we have gx to the power of n. Gx to the power of n. So we have y equals, well, let's say fx equals to gx to the power of n. What's the derivative looks like? G dash x. Yeah. Anything else? Times n. 3 components. Okay, n to the front, derive the inside, and reduce the power by 1. Okay, 3 components for using chain rule. So f dash x, we have half to the front. Well, n is the easiest one we can get, which is half, times g dash x. What is my gx? The inside is my px, right? I want to derive the inside. So to derive the inside, we have 2e to x. Okay, to derive the e to the power of 2x, derive the power, that gives you 2. Repeat it again. And then minus 1. That's my second component, g dash x. And the last thing is e to the power of 2x minus x to the power of negative a half. Alright, to the power of negative a half. You need to reduce the power by 1. Okay, reduce the power by 1. So that's the n, that's the g dash x, that's the gx to the power of n minus 1. So I can simplify it a little bit. The top is 2e to x minus 1 over bottom is 2 roots e to x minus x. Looks a little bit better. Okay. When I see negative a half, I want to make it 1 over square root or something. This looks a little bit better. Okay, you're trying to derive d. Okay, trying to derive d. Trying to remember, when you do things, do not put the formula beside you. Trying to think. It takes a long time at the beginning to remember it. But when you do it and then you're trying to, well, half guess, half confirm, that is the best way to remember the formula. You need to try to remember during you do the questions. If you always go back to the formula and then copy things down, you never learn. Okay, you never learn. And I would recommend, even though you have formula sheet in the end for part 1, part 2 exam, recommend not to rely on the formula sheet. If you use them, like it takes too long to go through the formulas, find it and copy it. Trying to remember as much as you can. finish, you can check your answer here. Derive the cosine is very tricky, the sine. You derive the inside, you get a negative 3. But the cosine itself will become a negative sine. Remember that? The sine to cosine to negative sine, and tangent to second squared. So you have, well, outside you have a negative 7. Derive the gx, you get a negative 3. And then cosine itself become a negative sine. So it's 3 negative, it's still a negative there. So that one is a little bit tricky. Give you a couple of more minutes to check it, or if you need rethink about it. Finish? You get it? Well, if you can't get it, you can ask me. Okay, let's look at a special one. Okay, let's look at a special one. This one. What kind of equation is that? Like, what kind of rule is that? It's exponential, right? It's exponential. But we can't derive it directly. We can't say that equals to 4 times 3 to the power 4x, because the formula we have can only works for base e. Okay, can only works for base e. So this is not base e. It is exponential. We need to somehow make it look a base e and then do it. So how I can change this to base e? Well, first of all, it needs to remain the same equation. Okay, can't change. Like 4 can't become e directly. So how we can make it in the form of base e? Give you a hint. Something we learned in year 11. A equals to e to the power of log ea. If you still remember that. A equals to e to the power of log ea. You need to use this to make 3 become a base e. Okay. Well, I'll show you an example first. You do the second one by yourself. So 3, okay, this number 3 is not good. Okay, I don't like it. I want the base e. So 3 will equals to e log e3. 3 will become e to the power of log e3. That's still 3. Okay, that's still 3. So fx equals to e log e3. Don't forget log e3 is a number. Okay, that's a number. It's not a variable, it's a number. That's 3 to the power of 4x. Remember that? The 3 to the power of 4x. I replace 3 by e log e3. Okay, and then what fx equals to? Fx equals to e log e3, 3 times 4x. Like what we use here is a to the power of m and then to the power of n. We have a to the power of mn. Well, looks a little bit, looks a little bit better. What we have is e to the power of 4 log e3x. Well, it's 3 things times together, so I can change all that. So 4 times log e3 times x. It's a linear. This is a linear. Can you see that? Well, 4 log e3 is a number times x. It's just like ax is a number. Now we can derive it because it's base e to some power. Okay, base e to some power. So what we have is f dash x equals to 4 log e3. Okay, derive the linear, just get the coefficient, 4 log e3 times e to the power 4 log e3x. We repeat that again. But e4 log e3x, that's just fx. So we can change it back to 3 to the power 4x. This is fx. Fx equals to 3 to the power 4x. Why is fx? Because here. Right, that is just fx. Well, we make fx at the beginning looks like this. So we can convert it back, simplify it. So what we have is 4 log e3 times itself. So 3 to the power 4x. Guess it still remains some feature of exponential, like the derivative will still contain the original equation. The derivative still contain the original part. So that still remain the same, some kind of the same factor, same characters here. So repeat it again. Yes, f dash x contain fx. All right. Any questions to this one? How we make it into base e? Well, if you don't have questions, I'll skip f. You do f as homework. You try that by yourself, because I want to talk about the log. Okay, for log, before you start derive it, every time you see a log function, you need to think, should I do something first to make it simple for me to derive? So 3 things you can apply to log. Log em equals to log em plus log en. That's the first thing we'll try. Can we do that? If we can't, we do it. If you can't, you do it. Log em over n. That is log em minus log en. Can we do that? If we can, we do it. We change the equation first. The last one is log em to the power of p. That is p times log en. P times log en. Can we do that? If we can't, we're trying to do it. Then you think about g, what we can do. What we can change first before we derive it. Well, I'll tell you why we do this first. Again, when you have times in between, it's hard to derive. Hence, you need to use product rule to derive. But if you apply the formula, that becomes a plus. It will make it easy to derive. You can just separately derive them and then add the derivative together. Same reason as the quotient rule here. Well, you need to use quotient rule to derive the inside. But if we can subtract it, we can derive it directly here. Well, to the power of p, we need to use chain rule there. We don't want to use chain rule even though it's easy to use. We drag the p into the front, that becomes the coefficient. Then you just times it with the derivative. So it's easy to do it. So for the first one, what you should do, what gx needs to look like. What's the square root gives you? Power of half. So which one we can use? The third one we can use. So the gx will becomes a half times log e, 8x minus 15. And let's see how easy we can derive this. How easy we can derive this. So g dash x will equals to a half times the derivative of log e 8x minus 15. What's the derivative for log e gx? 8 g dash x over 8x minus 15. Good. So over itself. So it's g dash x over gx. And that just gives me 4 over 8x minus 15. Can you see how easy we can actually do it? Like if you directly derive it, you need to derive 8x minus 15 to the power of a half. So the inside will become a half times 8 times 8x minus 15 to the power of negative a half and over square root 8x minus 15, and then we need to simplify it. Like it takes a long time. Okay, it takes a long time. Let's have a look at next one. What you should do to this one? Well, obviously I'm not going to derive it directly like this. I can't. So g dash x gives you, which rule we use first? Well, 1, 2, 3. Which one? Sorry. Second. Yeah, we use the second. It's a fraction. It's a fraction. So we use the second. So log e x squared minus 2x plus 3 minus log e 3 minus x to the power of 3. Can I do anything else? Yes? Sorry, which one? Oh, Jax's. Okay. What else I should do? Any other formula I can apply? The third one, yeah. So gx, well, the first part will remain the same. And then what we have here? Minus hover to the front 3 log e 3 minus x. Okay, bring the power into the front. Can you see how nice this function looks like now compared to original function? So now we can derive it. Log e gx, derive the inside 2x minus 2 over x squared minus 2x plus 3 minus 3 times, what's the derivative for log e 3 minus x? Negative 1 over 3 minus x. Okay, it's minus 1. 3 minus x, derivative is negative 1. So g dash x equals 2x minus 2 plus 3. Can't do it. Factorize. I'm trying to factorize. Plus a 3 over 3 minus x. Yes? Yeah, we times this 3 on top of that. Okay, it's circular functions later, but there's a log 1. Okay, there's a log 1. What's wrong with this equation? Base 4. Okay, base is not e, base is 4. What do you think you can do? This one is easier to change. You heard about change of base? Change of base? Yeah, log, what is the formula? Log AB. Well, change to base e, obviously. So it's log EB over log EA. Right? That's the change of base formula. Yeah? Log EB over log EA. So gx equals to log e x squared minus 4x plus 1 over log e a, which is 4. After change of base, your denominator will be a constant. You see, because we have a numerical number here, so log e of a numerical number, that's a constant. So we have a constant on the denominator. So gx is 1 over log e4 times log e x squared minus 4x plus 1. So I put the coefficient into the front, make you look a little bit better. So g dash x is 1 over log e4. Well, the constant remain the same, and you derive the inside. So that's 2x minus 4 over x squared minus 4x plus 1. Any questions to this one? This one's easy than the exponential one, like to change it. Change of base formula can directly apply, and you don't need to do much about it. So it's a constant on the denominator as well. So it's just become the coefficient at the beginning, and then you derive the inside over the inside. Okay, just do one last. Well, m or n, which one you choose? You choose one to do. M or n? Which one is more complex? Well, for m, like we need to use chain rule for both of that. So for px, this one, I'll just put the equation for you. So that's 2 times sine 2x plus 1, then to the power of negative 3. Remember I told you those 3 in the middle is actually the power, so it's the whole thing to the power of 3. So if I want to derive it, I make it to the power of negative 3. For this px, we will have 3 cosine 2x minus 1, and then to the power of a half. And then to the power of a half. Well, I think n is harder. Let's do n. So np dash x equals to, okay, gx to the power of n. We have n first, which is a half. We derive the inner function. What we have is 3 times, well, derive the inside, which is a 2 times cosine become negative sine, and 2x minus 1. Let's derive the inner function. And then you will times with the same function, but reduce the power by 1. You have negative a half. So remember, cosine will become minus sine. Yeah, cosine will become minus sine. So when I derive the inside, we have the 2, and then cosine change into negative sine, and then you still have the thing in the bracket. Okay, so that's n. So we haven't done J, K, L, M, and one question above is F. So 5 questions, you go to derive that tonight. Okay, and we check answer tomorrow. So 5 things. Any other questions? Okay. All right, just finished.